Hello, in this video we're going to learn about Kepler's laws and motion of things in orbit. So far we've already learned about universal gravity from Newton. Well, Newton based his laws off of Kepler's laws. And that was the bell for our afternoon announcements. So Kepler's laws are named after Johannes Kepler, born in Germany. He did a lot of things and pretty much laid the groundwork for a lot of astronomy, and Newton to come along and make his universal gravitation laws. So what are Kepler's three laws? There are three of them. The first one basically just says that things in orbit in ellipses, not in perfect circles. So anything that's like orbiting a star or a planet orbits in an ellipse. That means basically if you take a circle and you smush it down a little bit on two sides, you get a long radius and a short radius. So that makes an ellipse. It's a flattened circle a little bit. Second law says that these objects in orbit will sweep out equal areas in equal time. Well, that means if you get close to the object you're orbiting, you speed up a lot. When you get farther away, you slow down. But if you look at the distance that it travels over a period of time, so if we look at a month of the Earth's motion around the sun, and then you were to take kind of a pie slice of that orbit, so you take a piece of that ellipse, and you compare it to a month on the other side when it's going slower, those two areas will be exactly equal to each other. So basically, if this was a piece of pizza, these two pieces of pizza, even though they look different, would be exactly the same size, the same amount of pizza. And that's the second law. It's just saying that those areas are always going to be equal, no matter what the object is. It will always sweep out an equal amount of the circle or the ellipse in an equal amount of time. So that distance it's traveling is not the same, but the whole area of the ellipse, the whole area of the triangle, basically. Little brain break. Go ahead and read that. Ha, ha. Third law is an equation. Yay! The important part of this equation is just that it's relating the period and the radius of the object in orbit. The other really important part of this equation is this is how we get the masses of objects that are in orbit around something. So like if you wanted to know what the mass of Jupiter was, this is actually the equation we use to find Jupiter's mass. As long as we know how long it takes to go around the sun and how far away from the sun it is, we can find its mass. Sorry, another interruption. I love this. You guys are just going to hear tons of bells and announcements during this video. It's going to be great. So anyways, the m here is the mass of the object that you are orbiting. So, I was just saying that it's great. I just said that you can use it to find the mass of Jupiter. You can't. You can use it to find the mass of the sun. Well, either way, building on this equation and using universal gravity, we can find the mass of Jupiter. So those two equations combined, but it helps us to find that. But this whole piece pretty much becomes a constant. So this third law, the important part is relating the period and the radius of the object going around something. So the thing that's in orbit. And the really interesting part is if you divide this period by this radius, you'll get the same exact number for every single object that has an orbit. So like all of the planets in their solar system, if you divide their period squared by their radius cubed, you'll get the same number. And that's exactly what this chart is showing. So if we take all of the lengths of times their period for the orbits of all the planets in the solar system, including Pluto, yes, we included Pluto there just for the memory of it, and how far away they are from the sun, you divide period squared over radius cubed, you get about 1 for every single one of those. In fact, you would get exactly 1 if you actually used non-rounded numbers for all of these. So, ellipses, we need to know a couple parts of them, because otherwise you can't talk about an object being in an elliptical orbit. As I was saying, if you take a circle and you kind of smush it, so you smush it vertically here, you'll get a short radius and a long radius. So a circle has one radius. It's the same way around all the way around. An ellipse has two different radiuses, one that's long, one that's short. And don't mind the focus here. Those aren't even correct, so don't worry about it. The short radius we call the semi-minor axis. The long radius we call the semi-major axis. Now, orbits are actually a little bit offset from that. So the Earth going around the sun is actually not going around the sun being at the perfect center of the ellipse. It's actually just a little bit offset from it. It's actually not even offset by its entire radius, the entire radius of the sun. So just the exact center of the sun is off by a little bit from that center. And that's because all of our planets pull on the sun. So our gravity is making the sun move a little bit. So if we look at an asteroid where the sun is really far off of that center, we call that long radius. We have two different names for it now because it has a short distance to the sun and a long distance to the sun on that semi-major axis. The shorter distance we call perihelion. The longer distance we call aphelion. So they're just special names for the distances to the actual thing you're orbiting. So to sum it up, first law, all objects will orbit in ellipses. Second law, those objects sweep out equal areas in equal time. And third law, if you take the period squared divided by the radius squared, it's the same for every object that is in orbit. And of course, the third law is the equation, so we could use that to get other things as well.